What is up, guys? Welcome back to Vanover Machine and Repair, and welcome back to another machining video. In today's video, we're taking this 36-inch log, 6-inch diameter, 1045, and we're turning it into 8 large spacers. So let me bring you in close and give you some more details. For the material, we have this nice piece of 36-inch by 6-inch hot roll 1045. And we have a nice metric tape measure here for those of you across the pond, 91.5 centimeters by 155 millimeters. And this piece is going to be cut down into 8 individual spacers that our customer is going to weld on to a custom quick attach coupler that they're making. Now let's address one elephant in the room, and that is solid bar versus hollow. Every time we do a job like this, we get comments about why not just buy a hollow bar. The reality is that would be super nice. We can get hollow bar here in the States, but it's extremely expensive and it's usually special order. So unfortunately, in order to keep the cost down and the lead time down, we almost always opt for solid material, but that leaves us with a little bit of a predicament. And in this case, we're going to be machining away like 70% of the material, and drilling is fairly inefficient. I've been going back and forth on the manual lathe to try to figure out how we can drill it more efficiently, and honestly the answer is a spade drill, a U drill, an HMD drill, anything other than the old school method, but all those involve coolant, which we don't have set up. Now we are getting a new machine which does have coolant, and that will solve that issue, but in the interim we're going to be drilling these out the old-fashioned way, starting with a smaller drill bit and sort of working our way up. So to sort of make it interesting, I figured since I'm learning CNC, we would try to make a couple of these on the CNC, just the boring cycle, so we can see if that's going to save us some time, and we'll see how it goes. The first step is to put a center in the end. We'll get the OD turned down, and then once that's done, we'll start sawing these off over at the hide mech. We're ready to machine down the OD of this part. I think this is the most efficient way of doing this. I've done this job several different times, but I'm sure, like a lot of things, we'll improve our process along the way. I'm trying to clean this up in one pass. The tolerance on this is pretty much non-existent. This is like 6-inch 30 thousandths as it comes, and this is going to be a 6-inch part, but if it was 5 3/4, that would be completely fine. It's getting welded inside of a 6-inch-ish flame cut hole. So what we're going to do is we're just going to machine it down until it cleans up mostly and call it good. So we'll touch off, and we might take a couple passes over here on the end because it's not perfectly concentric. We'll get it cleaned up and then we'll go from there. At least in the beginning, we're going to start off with 6 inches. So we're going to take off 100 thousandths. See how she does. All right, you can see we didn't fully clean up here, and we're cutting a little bit of a taper, or at least it appears that way because our center was offset, but that's fine. We're just gonna take another 100 thousandths. Hopefully that'll clean this up, and we should be all good to go. Finish is turning out really nice. Had some problems with chatter here in the beginning, but we figured out a good feed and speed. We're still at 16 thou per rev, 380 RPM. We just needed to figure out a good feed rate and depth combination. This is a roughing insert, and overall I'm very happy with that finish. So we'll finish out this cut, and this should be finished up. After we got this bar cut up into 8 discs, my game plan was to do a couple of these on the CNC and a couple of these manually and time them so we could see which one was faster and more efficient. But we have an issue with the CNC machine, and I'm gonna give you an update on that, and then we're just gonna convert and do these manually in the meantime. And this is the first time really showing this machine in its entirety. So far it's been a really good machine, but I haven't done a ton of content on this guy just because I'm learning the machine, and I really need to cut my teeth before I'm giving you guys instruction on what I'm doing. But in regards to this job, I did have our chuck set up, and we were getting ready to take a cut, as you can see, but our spindle aired out. And the reason for that is the motor went bad on this CNC. Now it's the main drive motor, and so we were able to pull it off, and we're in the process of rebuilding that motor. As you can tell, we got it fully apart. It seems pretty typical over here in my shop that we're rebuilding equipment, even equipment that seems to be fine. And we've already done 4 motors in the last 6 months, so what's the 5th one? So we got this one torn apart, we got new bearings in order, we had an electrical issue that we went ahead and sorted out, and we're gonna go ahead and put this back together off camera. And as a result of this downed machine, we're gonna focus on making these bushings manually. So we're gonna get back over to the pacemaker and talk about our setup over there because it's a little bit unique, and then we'll go ahead and get these bushings knocked out. Keyboard warriors, get excited. We got something you're not gonna like. Drilling over here on the pacemaker, and we're doing a non-ideal setup, but I wanna hear those comments. I wanna learn, I wanna get better, and we're gonna get to the point where we're doing this correctly. We're just not there yet. We're making do with what we have. So in this case, we need to punch a 3-inch hole in 8 parts. And if you did this the traditional way, you could get it done, but it would take a decent amount of time. You'd center drill, pilot drill, drill one size, drill a second size for a large boring bar, and then bore the rest. It would probably take, 40 minutes per hole, and it would be, a lot of drilling over 8 parts. So we're looking for a more efficient way, and the more efficient way is a spade drill. Now the problem with spade drills is twofold. One, they have high tool pressure, so you can't run them on weak, non-rigid machines. Well, we got that covered. This machine is rigid and it's got tons of power. So that's great. But the second problem is you really need to run them with coolant. And this machine does not have coolant. And that's a major problem. And the reason for that is high-speed steel, which is what I started with on these spade drills, burns out because we're not running coolant. So I switched to carbide, and carbide does hold up, but eventually it chips out and is less durable, and we're blowing through $50 or $60 inserts, and that doesn't make sense either. So we're really between a rock and a hard place, and the answer is coolant. And we're going to solve that because we have a new machine coming, and that does have coolant. But until then, we still need to get these drilled, and I'm not going to go and center drill, pilot drill one side, drill a second, drive, and bore each of these 8 spacers. So here's where we're at on this specific job. And I want to kind of get your feedback because it seems to be working, but it's definitely not ideal. So I went ahead and done 4 of these spacers off camera testing this method. But what we do is we come in here with a carbide spade drill, dry, no coolant. And this spade drill actually works pretty well because it's carbide, so it takes the heat and it has a lot of support on the tool. Because the insert is so close to the body, and this is a 1.5 style, which indicates the insert is close to the body, the insert lasts longer. These bigger spade drills have the ability to, or tendency to, overhang from the body because these bodies have a wide range of inserts they can accept. And because we're not running coolant, and because these overhang, they are much more likely to chip at the ends, and they do that. So this smaller drill is better supported and it holds up better. So we're going to come in here and drill a pilot hole, which is not required with the spade drill, but what it does is it reduces the tool pressure of this next size drill because this is quite a big drill. Once we got that pilot, we're going to take this HSS cutter and we're going to run this at a slow RPM. It's going to feed in at a really low feed rate. I think it's like 3 or 4 thousandths per rev. But because we're turning slow, we keep the heat down, which means we don't burn up the cutter, and we get our hole drilled, and we can drill a hole that's about 2.5 inches in about 10 minutes after we pilot it. So with that being said, let's get a pilot drill in this material, and let's get to drilling. Step 1 is to get our tool holder installed and indicated in. Now I could indicate this traditionally, but that takes time, and if you're switching between tools, it can take too much time. So I've come up with a quick and dirty method that works pretty well. I've went ahead and turned down an 1.5 inch circle and slid it into a really nice fit on this Morse taper extension, and then I can take my tailstock and slide it through this and clamp down, and that will tell me that I'm dead center. Then I can zero my DRO, back my tailstock out, and I know positionally I'm good to go this way. And because this is nice and square to the bed, I know I'm also good side to side. And by doing it this way, I can set up for drilling in about 2 minutes compared to 5 or 10 minutes it would take to dial this in if I used an indicator and tapped it around and adjusted the height using a center indicator in the chuck. And ultimately, I did that before, but I think this is a much more efficient way to do it, and it gives us a good result. The other thing is I've noticed is getting this dead nuts on center isn't actually that critical because you have backlash in the machine. We get it within 1 thousandths or 2, and as you make a cut, this cross slide is actually going to kind of float and find a home because there's movement in the carriage, and these center drills have a very specific center point. So if you're 5 thousandths that way and you have backlash, you know, your carriage or your top slide or your compound or whatever is going to move over and find center where it's happy. So we get it extremely close with this, but even if it's off by a few thousandths, it's not going to matter anyway because of the movement we have in the top slide. With the explanation out of the way, we're going to get straight to work. We're going to tear our tooling setup down. I'm going to set up a timer, and we're going to see exactly how long it takes to set up the tool and punch out this hole. All right, here we go. Start the timer. All right, we need to get our tool post dialed in. We're going to drop this guy on here. There she is. Snug her up. I'm going to lock this down now. Looks good. All right, we're 1 minute in. Got our tool post indicated in. All right, we're going to remove the drill bit. Get the right one in there. Lathe is on. 445 RPMs. 4 AD. 4 thousandths per rev. And 0 RDRO. Power feed on. Let's remove our pilot, install our large spade. We're going to set this to 105 RPMs, same feed rate. Looks like we're about 5.5 minutes in. There we go. As you can see, we have a good chip formation here. This is working out nicely. Taking a look at the DRO, you can see it's moved 0.8 since we zeroed it. Took about 20 minutes to punch that hole out from the start to finish. Honestly, I'm fairly happy with that given the diameter and the depth. We're going to go ahead and jam out the other 3 off camera, and then we'll bring you back for the boring operation. Time for the boring part of the video. Getting all these holes bored out. Now, I don't want to make a mistake here. 4 of these are going to be one size hole, which is 82 millimeter with 2 millimeter of clearance for an 80 mil pin. And 4 of these are going to be 102 with 2 millimeters for a 100 mil pin. So we're going to start by boring these out. We're going to see if we can do this as fast as possible while still getting a good finish. So we're going to chuck up a CNMG boring bar and see how deep we can cut. We're running a 1.5 inch CNMG boring bar. We're trying out a new insert here. We're going to start nice and aggressive, 750 RPM, and we're gonna start at 18 thou per rev. This is at 62 millimeter. 20 millimeter needs to come out. We need to come up to 82. So let's get this bad boy started. See how fast we can eat away material. So we're gonna touch off. See how that does. Seems to be fine. See how she does. Now, wants to stall the machine. I want more. I'm going to slow it down. 445, because I want to take a deep cut. See what we got. There we go. That thing's getting to eat. And I think that's a little much for that insert. All right, here's our guy right here. ISCAR 8250 grade, MP4 chip breaker. These are bad to the bone. Let's see if we can do what we were trying to do with that last insert. I think it's a 433. Might be a 432, I have to check. All right, 8 mil depth of cut. Let's see what we got. Actually, it's about 6 mil. See what you think. All right, we got that bored out in like 4 passes. We're at 80-ish millimeters. I've been doing this job several times, and the best technique that I found is to go ahead and rough all of them out, and then we'll come in here and we'll clean all of them up with a finish pass. That'll just ensure we have a nice smooth bore, and it's an extra operation, but if we assembly line it, we get most of the roughing done, which is where a lot of the chip packing up is, and then we'll switch to a D&MG style bar, and that'll get us a better finish, and we can go in there and take out the last mil or two. We're working on these 102 millimeter holes. I switched over from a 432 to a 433. This is the insert right here, so it's a C&MG 433 M3P chip breaker, and it's an IC 8250 grade ISCAR. It seems to be working pretty well. This is really, really hard on the inserts, and we're just roughing it, so you can tell that the finish is pretty bad, but you can see we're taking 5 mil total cut, and we're moving at 15 thousandths per rev or 18 thousandths per rev. So it's not the most ideal. The main problem with doing this is chip evacuation. I was using air. Air works pretty well, but the air just gets annoying over time, so I was stopping it and just adding air only when we need it. About halfway through the cut, I'll do an air blast. So let's go ahead and continue on. Honestly, this is super boring stuff, guys. Nice healthy cut. So we're going to come in here and bring us right to 82. Tolerance is plus or minus 1/2 mil. Not critical, guys. That's going to be like 2 mil. All right, 1 down, 7 more to go. Come in quick, come out quick. That's it. Now we'll chamfer the inner bore. That's it, nice and quick. We're gonna get this flipped around. Make sure we're cleaned up here. Be able to register off the chuck. So now we're going to bring the insert over to the chuck and 0 off. And the larger ones are going to be 3 3/4. That's 4. The nice heavy cut. Good surface finish. Good chip load. Just like that. This spacer is done, minus the hole. Turned out really, really nice. We're ready for our last operation over here at the radial drill. I absolutely love this piece of equipment. It puts holes through material nice and efficiently. We're using an HSS 22 millimeter drill bit. This drill bit is clearance, very heavy clearance for a 3/4 bolt that they use. Again, like everything else, the tolerances are very rough. We use a little trick to align the drill bit on center. So first, I went ahead and made a mark. So this is a 7/8 drill bit. by 7/8 in from the end. It's 22 millimeter, but it's close enough for this job. And what we'll do is I will get it basically on center, or what I think is center, according to my mark. And once it's good back and forth, I will lift up the drill bit and we will get our scale ruler on here. With our scale ruler on here, what we'll do is we will move this head back and forth until we are level. And we're ready to drill. We're going to use some of our green magic just to get started. Running 252 RPMs with a feed rate of 8 thou per rev. Four more to go. We have our nice little stop here set up. Well guys, we got the spacers done and I think overall they turned out pretty dang good. We did have some problems with the CNC machine that were unexpected and we did struggle with the drilling, but I think this version of these spacers or bushings were much better than the last one in terms of efficiency. And on the next set, I hope to get even more efficient and get a better product. Now with that out of the way, let's talk about some of the struggles that we did have and maybe some ways we can overcome that in the future. Now for those of you who want a little more explanation on this job particularly, let's talk about some of the difficulties of doing this job and maybe how we can be more efficient in the future. Now this job does seem fairly straightforward on face value, but the main issue really is work holding. The first couple times I did this job, I left another inch or two of meat on each bushing so I could grip the part. That allows me not to damage the exterior surface by gripping onto it, and it makes sure that the OD and ID are concentric. This go around, I opted not to do that, and we instead machined the OD first, chopped them up, and then gripped on the OD so that way we could flip the parts around and do all of our subsequential ops. In that case, what we did is we damaged our freshly machined surface with 3 jaw chuck marks, which I knew would happen, but we were able to be a lot faster on the job, and we also probably have about 3 to 5 thousandths of run out between the inner hole and the outer hole. I think for what we're doing here, that was a great compromise because it allowed us to save material and be a little bit more efficient. But I'm curious if you guys have a better way to do that. Let me know down below in the comments because it's a game, right? If we want to machine this and save some material and scratching, we leave a little bit of extra, but it comes at a cost. Now the second thing that makes this challenging is the drilling. Now I know I'm going to get a lot of comments, why don't you buy a hollow bar? That's fine. We can get it, but it has a long lead time and it's really expensive. It's actually cheaper to pay for the labor to hog these holes out and get cheaper material than it is to wait for the more expensive material. So that leaves us down to drilling. Now you can see that these parts are probably half of the weight that they were when we started, and that's rather inefficient. And drilling holes is the most efficient form of machining. However, I am not properly set up to be efficient with this. The 100% best, most efficient way to drill these holes is with an HTS drill or a spade drill with coolant. We didn't have that. We struggled. We did get it done, but I'm hoping in the future we can have one or both of those methods so we can punch these holes out quicker and waste less time boring and drilling and boring on different sizes. But overall, other than those two issues, everything worked out pretty good. I hope you guys enjoyed the video. Let me know your thoughts down below in the comments, and I'm gonna get these parts shipped out to the customer. We also have a little bonus section at the end of this video where we talk about some upcoming projects that I think if you've made it this far, you'll probably be excited to hear about. So stick around for that, and until next time, we'll see you in the next one. I'm super excited because in the summer, we're gonna be releasing 2 major video series that are outside of the normal realm of what we do on a weekly basis. The first one we already shot, and we had about 7 or 8 viewers come up to the shop, and we spent 2 days doing a crazy thing. We filmed it. It's going to be awesome. I'm going to be a little tight-lipped on that one, but trust me, it's worth the wait. The second video series, I'm going to tell you exactly what I'm doing, and it's going to be a ton of work, but I think it's going to be well worth it. But I need your help. Last year, we did a video on which lathe to buy, and a lot of people benefited from that video. It was all talking, no working, and we just broke down a lot of the tips and facts. This year, I'm going to be upping the ante, and we're going to be doing a video on comparing multiple machines, and I'm going to get at least 6 different lathes in the shop, different swings, different brands, and compare all the way down to a hobbyist lathe, like a mini lathe, all the way up to a 25-inch swing, and everything in between. And we're going to put them through a battery of tests to compare and see what type of lathe do you actually need. Differences between the higher end brands and the lower end brands, bigger swings, smaller swings, etc. In order to make this video successful, I'm gonna need 2 things from you guys. The first thing is I want you guys to give me your feedback. Now I have my own ideas and thoughts on how we should compare each machine, but I want to know what your thoughts and your questions are and how we can sort of test each machine head to head. And I'm going to do my best to compile all that feedback so that way when I make the video, I can address your concerns, my concerns, your thoughts and my thoughts, and try to make this one long, effective, successful video. So that's the first thing. The second thing that I need from you guys to make this video great are some lathes. Now I already went out and purchased this beautiful South Bend heavy tin so we can use it in the video, specifically because I know how popular the machines are and how much you guys love those machines. We already have the Colchester and we already have the pacemaker, and we are getting a new secret machine that we will be comparing as well. But ideally, I'm looking for some type of Monarch to have in the video because I know how popular the Monarchs are, and I want to see how they stack up against the pacemaker and the Colchester and the South Bend and a couple other models. We did have several viewers reach out offering a Shoreline lathe, which will cover our mini lathe section, and an Inco lathe, which will be a little smaller than the one we have behind us, which is nice. But ideally, I'm looking for a little bit more lathes in the medium to larger size category, maybe similar to the pacemaker to compare with. So if you have any of those 1940s or 50s Monarchs laying around that you'd love to be featured in the video, give me an email or shoot me a call or text and let me know, and maybe we can work something out. Now, to be clear, I am not over here trying to get a bunch of free machines. Frankly, I have enough lathes in the shop, and even this lathe behind us, once we're done with the video, we'll be parting ways with it. But if you have any machines you are looking to get rid of or you don't mind loaning out for a few months, let me know and maybe we can work something out. Now, we are here in Chicago. I had a couple people reach out 5, 10, maybe even 15 hours away, and something like that isn't going to be feasible, especially when the machine's 10,000 pounds and we're taking it over the border. But if you're within, a 4 or 5 hour radius and the machine is going to be a good candidate, let me know. Now, we're not looking for projects. I had a couple people show some footage or some videos of some machines sitting outside. That's not what we want. We want something that's running and that's going to be a good example so we can put it against these other machines. If there are some things wrong with it, like there were with this, we can fix minor stuff, but just due to time and due to us shuffling 6, 7, 8 lathes, we don't want each machine to be a project or the video will never happen. So again, my email, vanovercustoms@gmail.com, my phone number, 847-890-9969. Shoot me a text, shoot me an email, give me a call, and let me know. Other than that, I hope you guys are looking forward to that video as much as I am. I think it's going to be a blast. It'll be a ton of work, but it's going to be worth it, and it's going to be great. And we'll see you in the next video.